Hello and welcome to the Daily Space for today, Thursday, March 5th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today's top story builds on an ever-growing body of research that seems to indicate the evolving chemistry and stellar populations of our universe may cause type 1a supernova to, on average, look different as a function of when they existed in our universe. If this is true, it may be that dark energy can become a nightmare of the past as our understanding evolves to not require it. In a new paper in Astronomy and Astrophysics, a team of Max Planck Institute for Astrophysics researchers, led by Maria Bergman, looked at how the abundance of manganese has changed over the course of history, with generations of supernova adding it into the universe. In their study of chemical abundances of 42 stars in our own Milky Way galaxy, they find that the ratio of manganese to iron stays constant with time. Since these two elements are created in very different ways, this means that on average, the processes that produce one happen as often as, the methods that produce the other, like two different factories working on similar production schedules. In looking at all the different ways that manganese can be formed, they realized the only way they could explain their observations is if 3/4 of all type 1a supernova explosions of white dwarf stars that have occurred in our galaxy are, non-standard supernovae. When we typically talk about supernova type 1a, we assume that it's a system where a moon-sized white dwarf star is orbiting a giant star and slurping off its outer atmosphere with gravity. When the white dwarf star has consumed enough of its neighbor to top 1.4 solar masses, the white dwarf explodes. This is because a white dwarf can't support that much matter. But as we've recently pointed out, white dwarf stars can find other ways to go boom. They can merge into their companion star, triggering a double detonation of both stars as they destabilize. They can merge with another white dwarf. They can actually merge with pretty much whatever they please, and in each of these myriad of scenarios, they can go supernova, and they will often detonate their companions as they go. The new research coming out of the Max Planck Institute for Astrophysics finds the chemistry of our galaxy is consistent with these double detonations being, the primary death explosion of white dwarfs. If this is the case across our universe, then our measurements of the expansion of the universe are based on, a solidly false assumption. And, type 1a supernova aren't as simplistic as we've been treating them. Research like this requires replication, and a team at Caltech has already started to see similar results in looking at stars in dwarf galaxies. The next Gaia mission data release should help identify more white dwarf binary systems, allowing us to understand just how common these kinds of systems are, and to directly determine, just how common type 1a supernova of two white dwarfs might be. For now, this is one more observational line of evidence, indicating we don't understand our universe as well as we thought we did. And dark energy may someday be the thing our generation of astronomers is laughed at for theorizing. At least one can hope. From stars dying as supernova, we now turn to stars dying as planetary nebulae. A team of astronomers using the Atacama Large Millimeter Array has found an aged star not too different from the Sun that is just beginning to exhale its atmosphere. In this image, we can clearly see in blue high-velocity jets blowing from the star's poles and interacting with dusty clouds that are shown in orange. This is a system just starting to form a planetary nebula. And in a new paper in the Astrophysical Journal, led by Daniel Tafoya, they postulate that the high-speed jets may have turned on just in the past 60 years. There are people watching this right now who've been around longer than these jets have been around. This object was part of a large survey being conducted to try and catch planetary nebula in all stages of formation. And if we're lucky, ALMA will allow more of these baby systems to be found. From star deaths, we now turn to spacecraft with 2 quick updates. The first is a bit frustrating. NASA is updating the 70-meter radio antenna in Canberra, Australia, and it needs updated. But this antenna is used to communicate with the Voyager 2 and other missions, while other closer missions can also chat with smaller dishes. Only this great disk is capable of sending the powerful signals needed to send new commands to Voyager 2. It's estimated that the upgrades will take about 11 months to accomplish. And during that time, we'll be able to receive data from Voyager 2 using other dishes. But while we can listen, we won't be able to talk back. This shouldn't have a major impact on this distant mission, but if something goes sideways and Voyager cries out for help, we're not going to be able to respond. So here's to hoping that things actually finish ahead of schedule. In more cheerful news, the OSIRIS-REx mission did a 250-meter flyover of the Nightingale site on Bennu. This is the primary choice of sample site, and this flyover not only got them better data, but it also allowed the mission team to practice the slightly crazy maneuvers that are needed to pass close to the asteroid's surface. While we haven't seen these new images, we can tell you they are full of rocks. All joking aside, OSIRIS-REx is designed to collect objects 2 centimeters in size or smaller, so much smaller than an inch. And these new images will have sufficient resolution for the mission team to figure out if this kind of debris is present in the sample site. Bennu is turning out to be rocks on boulders surrounded by rocks with granular material of every size scattered in between. And that rounds out our stories for today. I will now hang around and answer your questions. Please remember to use that purple circle with a purple star in the center. While you type them in, I'm going to remind you once again, I am Dr. Pamela Gay, and I have been your host for today, and I wrote this episode. Susie is taking a much-deserved day off, so if the production's a little shaky, blame me. All right, we are a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our universe and beyond. We are here thanks to the generous contributions of people like you. Please share what we create, get other people listening. You never know whose life you're going to change with science. If you'd like to support our continued efforts, please consider giving over on patreon.com/CosmoQuestX. We're able to do everything we do thanks to your bits, your subs, and your donations. Thank you for allowing us to, be here day after day. Now, one question I know has come up is, will we be covering the Mars naming release? And to be honest, I have mixed emotions on this one, and it's a weird kind of mixed emotion. A couple of years ago, when they put out the call for proposals for someone to run this naming contest, thank you for the sub, Tom Van Scooter. Thank you so much for that sub. Okay, let's make it rain. Okay, there we go. Let's see how long it takes the dogs to find all of them. So a couple of years ago, when they put out the call for proposals for someone to run this competition, they actually put it out as a, please submit an application to do all this work without being paid, and we will select someone competitively to do all this work for the honor of working with NASA. Now, I don't know if that's how it ended up being run in the end. I haven't followed this, but the idea that, this is something that someone wasn't paid to do, it just kind of bothers me. It's like you should never ask an artist to do work for exposure. Well, you should never ask an educational organization to do work for exposure. But that's what NASA did. So I have mixed emotions, and I haven't decided if I'm going to suck up my mixed emotions or not and watch online. So that's where it stands. Sorry about that. All right, so let's see what all is in the chat. Larry asks, did you see OSIRIS-REx discovered a black hole? I did. I haven't had a chance to go find the paper on it yet. I need to do that. But when is that ceremony? 2 p.m. some time zone later today? Yeah, really haven't been following. All right, let's see what other questions we have. So Larry asks, did you hear about the protein inside a meteorite? Yes, we mentioned this in passing on Tuesday. There is a meteorite found that is chemically believed to have originated in a solar system other than our own. And one of the side effects is, well, this allows us to understand if what we find here can exist out there. Oh, thank you, Svartmaya. Thank you so much. That you are awesome. I don't know if your name implies you speak Russian, but if you do, большое спасибо. Большое спасибо. Okay. Make it rain. Okay, I was distracted. Yes, protein in a meteorite from another solar system. This meteorite doesn't chemically match our solar system, so it's thought to have come from another solar system, and it has in it proteins that could have formed naturally, no life required. And this indicates that other solar systems have chemistry consistent with the formation of life. This is the second time this question has come up, so I'm thinking I'm going to need to cover that story tomorrow. I love Veronica Cure's question. Can Voyager talk to Voyager 1 if it gets lonely? No, the two Voyager missions can't talk to each other. My gain is too high. Oh, I can fix that. So I redid my studio so that I can actually read things way easier. I'll post pictures later on. It's a much happier setup, but I'm still working out the kinks. All right. Let's see what else is in here. Hanny asks, if there are 2 times the explosions, why didn't we notice something amiss previously? Well, so the way that we figure out these explosions is their light curve. How do they brighten and fade? And if both of the explosions in this kind of a double detonation model are powered through the same mechanism, they're going to have the same rise and fall pattern in their brightness. So the problem is, same physics, different scenario. It follows the same pattern of brightness. But where we thought that same pattern of brightness always had to have the same core luminosity, so it would be like if 100-watt light bulbs all slowly faded in and out in one way and 60-watt faded out in another. If you see a particular brightening and fading pattern, you assume 100-watt or 60-watt. But it turns out that occasionally the 100 watts can act like the 60 watts, and the 60 watts can sometimes act like 120 watts, which we didn't even know existed. It's a thing. The universe is super creative in the ways that it finds to confuse us. This is why we do science. Let's see what else is in here. Ruff's Matt says, a non-standard type 1a supernova. Well, If we are looking at supernova explosions in the Milky Way, all we can observe is the remnants. All actual supernovae are in other galaxies where the chemical balances might be different. So what we're actually looking at is old stars that formed from the remnants of supernovae. And the question is, what kinds of supernovae had to exist to get the observed metallicities we see in stars at different ages? So what this team did was they looked at 42 existing stars, measured their chemical abundances, knowing that they formed at very different times in the history of our galaxy. And they looked to see, so what kinds of supernovae were required to create these different abundances? And what they found is all throughout time, at least in our galaxy, the amount of manganese was proportional to the amount of iron, even though these things are generated in completely different ways, which means that you have to figure out how, with a standard proportion of stars, a standard population of stars rather, where you have this constant tick of iron being produced in the biggest stars, how do you get that same constant tick of manganese being produced? And the way they figured it out, well, the only way they could figure it out was if there were a lot of these double detonation systems going off that would form enough manganese. So we're tracing it out by figuring out what was required to make the stars we see today. I hope that helped. It's a confusing story, but it's kind of awesome. Sorry that I'm loud. Sorry. Okay. Let's see if there's any more questions down at the bottom. Now a bit low. All right. Let's try increasing 1. I have increased 1. I went down 3. Let's see if we can zero in on the correct gain level on the microphone. 5 for 5. All right. So I now know where I need to be. Are there any other questions? As a reminder, tomorrow we are going to be bringing you an episode of Astronomy Cast after the Daily Space. There will be a gap between the two. Tomorrow's topic is Katherine Johnson. And next week, we're going to take off because we have no clue quite what's happening the week after. Officially, the Lunar and Planetary Sciences Conference has been canceled due to coronavirus. Now, what we're trying to figure out now is there a way that we can track down the people doing some of the best content and bring them to you here anyways? Can we stream them in? Can we figure out, well, a way to keep the science flowing? So next week, instead of bringing you the Daily Space, we are going to, well, descend into chaos and figure out, well, how to get the best new science out of planetary science coming to you the way it should. So Henny asks, how many papers will be needed to kill dark energy for good? Could 2020 be the year? I don't think so. So sometimes you have to wait for people to die. And I know that's a very bleak statement, but they've already given out the Nobel Prize for dark energy. And so there are some people out there with a very vested interest in keeping it alive. I honestly think it's going to take Adam Rees, one of those Nobel Prize winners, figuring out exactly how to explain the discrepancies we're now observing in the Hubble constant for this to go away. Because as long as he's out there saying, no, we need dark energy, but also saying, but there's something weird with the physics, people are going to be arguing for a change to the physics. And yeah, I think it's going to take a little while longer. I'm worried it might require the James Webb Space Telescope's observing capabilities and its ability to see individual supernovae at significantly greater distances and potentially measure their chemical abundances. I'm hoping that's not the case. It's never good when you have to wait for people to die to do your science or wait for spacecraft to launch to settle an argument. But that may be where we are. Brexit denier. This iron and manganese thing, is the energy required to fuse these elements the same or very different? I don't know the energies, but they are formed in very different places. Iron builds up in the centers of massive stars as they near the end of their life, when they end up with an iron core, fusion that releases energy is no longer possible, and the stars die as type 2 supernovae. Manganese, on the other hand, is created in all sorts of ways and in different proportions in all the different ways. The only way to get the amount of manganese that we're seeing is if there's essentially a whole lot of type 1a supernova that form an assembly line of manganese, getting it into the needed proportions. So they're formed different ways, and we see them in different ways. I don't know exactly when the Mars 2020 naming thing is. It's at, I think, 2 p.m. in some time zone, but I don't know which. Someone may be able to Google this. Larry asks, have you heard of the D-star hex quark dark matter particle? No, I haven't. I'm gonna copy that and look it up later. All right, let's see what that allows me to find later. Thank you for the link. I don't know that particular site. Something just occurred. Thank you, Awareness, for the follow. You have a disturbing username that our mods may object to. Just saying. Mars naming gossip on Discord. Go ahead and check it out. Oh, it's happening in 7 minutes. All right. Rover McRoverface is not on the list. So it's happening 2 p.m. East Coast time in 7 minutes. No, wait, that would be 1:30. I'm so confused. All right, go check it out on Discord. I'm just going to shut up because I don't know. Okay. So I think the problem with Calypso is it's the name of another object. I don't know all the guidelines. We'll report whatever the name is tomorrow. For now, I will read what DPI 209 has posted. These 9 contenders and the students who proposed them are Endurance by K4 Oliver Jacobs of Virginia, Tenacity by K4 student Iman Riley of Pennsylvania, Promise by K4 student Amira Shanshiri of Massachusetts, Perseverance by 5 through 8 grade student Alexander Mather of Virginia, Vision by 5 through 8 student Hadley Green of Mississippi, Clarity by 5 through 8 student Nora Bennett of California, Ingenuity by 9 through 12 student Venice Rapani of Alabama, Fortitude by grades 9 through 12 student Anthony Yoon of Oklahoma, Courage by grade 9 through 12 student Tori Gray of Louisiana. Now, one of the problems with contests like this is they allowed any name that was under 50 characters and had not already been used for a mission and was not copyrighted, and there are a few other guidelines. Now, this isn't to say that these are the only students that put these names forward. It is simply that these students have been selected as the representatives of these names put forward. I believe they also had to explain why they selected the name. So this is just I have problems with these kinds of competitions. I'm just going to lay that out there. I have problems with these kinds of competitions. Yes. I should go eat lunch and record the podcast and stop being grouchy on stream. We will report the name of whatever wins tomorrow, and we will bring you the science as it continues to come, except for next week. We'll do a rehash afterwards of everything going on. So, with all that said, I am going to simply remind you all, wherever you are in the world, have a fabulous morning, evening, or afternoon, and wash your hands. This has been The Daily Space, a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. Bye-bye.